Hi everyone, welcome to week 3, and today we're going to introduce probabilities, finally. This is going to start the most challenging part of the class, which is really learning the basics of probability theory. But before we go there, let's motivate again quickly why we're going to do this. Why are we looking at probabilities? Here's a quick refresher. Last class we saw that we're susceptible to a bunch of biases. The gambler's fallacy, the conjunctive fallacy, etc. And I just gave you a little taste of the cognitive shortcomings that humans have. Humans are, in many cases, really bad at reasoning. So, what our inductive logic will help us do is partially overcome these. And the mathematical framework that we're going to use is probability theory. Okay, in constructing the inductive logic, we want to be as close as possible to our deductive logic, right? The deductive logic is, you might imagine, the gold standard. In our inductive logic, we want to be as close as possible from it, right? It can't be exactly it, because in deductive logic, the conclusions in a valid argument are guaranteed from the premises, but you can't get that in inductive arguments. Okay, so truth tables, remember, help us determine the truth value of a complex statement given the truth value of its simpler statements or elements. In other words, if we know the truth value of the simple elements, then we know the truth value of the complex statement. Right? Remember, this is just truth value and truth table basics. But deductive logic, remember, tells us nothing about the actual truth value of statements, right? What you care about is whether the conclusion is guaranteed from the premises. Similarly, with the probability calculus, which is the probability theory we're going to look at, what it will allow us to do is to determine the probability of a complex statement once we know the probability of the simple statements. But it won't tell us how to determine the initial probabilities. In other words, just like deductive logic doesn't tell us whether a statement is actually true or not, inductive logic is not going to tell us what the actual truth or actual probability of a statement is. This is important. It's an important thing to know. What is the actual probability that we should assign to a statement? But the mathematical theory of probability won't really help us do this. But that's fine, because what we care about is the logic. Okay, so just a few more notes. What we're going to be concerned with is the probabilities of statements. We're going to assign probability values to statements, just as in deductive logic we would assign truth value to statements. The mathematical theory that we're going to use is often called the probability calculus or probability rules. Okay, so after all this, let's look at the rules. And just a quick note, we're going to want to conform to deductive logic as close as possible. So you'll see that we're going to use some notions that we use at the beginning of the class and apply it now. Now, again, this is going to be some mathematics, so I recommend you go through this video slowly and try to really understand everything I say before moving on. It will really help you. Okay, so let's get started on probabilities. Now, what we're going to do is to show you the basic kind of foundations of the theory, which the theory will then build off of. Okay, so look at this square here, and there's a sign which is called omega. And what omega does is it represents all the possibility space. So what this does is that you can imagine that everything that can be said can be fit into this omega. So let A and B be statements, okay? And let's put them like this, represent them in this way, this Venn diagram. Now I can ask you, what is A or B in this omega? How would you represent it? Like, if you had to color, what would you color? Okay, I recommend you pause and think about it. Okay, so it'd be this red part. So you'd color both A and B, right? Because in A or B, remember, A or B is true when just one of them is true. So we note that A here is the red part and B is the yellow one. But if you land on the part of A that doesn't intersect B here, then it's still going to be included in A or B, because if A is true but B is false, then A or B is true. And here, if landing, say, on the red part of A over here, it means that, oh, that's A is true in that possibility space. And so you have A in red here, and then you just add B. Okay, what about A and B? What would you color here for A and B to be true? Would it be the same as before? Well, no. A and B would just be, you just color the intersection of the two. For A and B to both be true, you have to be, you might say, in a world where both A and B are true. So if before you go into the gray part of A or the gray part of B, then A and B won't be true. A or B would be true, but not A and B. All right, so let's get into probabilities. We denote the probability of a statement A with PRA, like this. Or sometimes you'll also see P of A. Now, if you say that P of A is equal to 0.5, that is, the probability of A is equal to 0.5, I'm going to mostly use P of A in this class because that's usually the standard notation, but I put the PR there at the line above because just so you can really get the feel that this means probability of A. So if we say that probability of A is equal to 0.5, that means that there's a 50% chance of A being true, right? And so the maximum that you can get in probability is 100%, so that would be 1. Now, why are we using probabilities, you might ask yourself at this point? Why, to make the inductive logic, are we using probabilities? Well, remember that the definition of an inductively strong argument is one in which the conclusions are likely or probably true given the true premises. But we're going to do something more. We're going to argue that our beliefs should correspond to these probabilities. And we'll make that more precise in the next lectures. But to do that, we really need to get the foundation of probabilities. Okay, so let's get started with some intuitive examples. What is the probability of a fair dice, landing on 1? Now, a fair dice is just like a regular dice that you might find at a casino or in the bottom of your drawer. What's the probability of it landing on 1? Well, we can represent it like this. The probability of the statement, the dice lands on a 1, is equal to 1 over 6. And this is around a 70% chance, right? So it's just 1 over 6, right? There's 6 sides, so the chance that it lands on one of the sides is 1 over 6. Now, what is the probability of a fair dice landing on an even number? Okay, that already requires us to do a little bit more work. Okay, so a dice has 6 sides, and it has 1, 2, 3, 4, 5, 6, right, as their numbers. So what's the probability that it will land even? Well, here, already it's starting to be more complicated. Maybe it's a little bit intuitive for you, but the probability that it lands even is 1/2, so it's around a 50% chance. If you don't immediately see this, think that there's 6 sides to the dice, and there are 3 even numbers, 2, 4, and 6. So the probability that it lands on 2, 4, and 6 is going to be 1/2. And we're going to make that more precise too as we go on. Now let me introduce a bit of terminology that we've already seen a little bit when in other lectures. So a tautology is a statement that is always true no matter what the facts are. Right? Remember then, a tautology, the truth table of a tautology is always true. That's what we mean by no matter what the facts are. It's always true. So there's no place in the truth table in which the truth value is false. Here's an exercise. Can you give me an example of a tautology? We've seen some in our exercises, right, in our homework and quizzes. Can you come up with one right now? Please try. Okay, one of the most simple tautologies that you can come up with is P or not P, or A or not A, right? P here stands for a statement. And I'm going to show you the truth table over here. We draw the truth table for P, then for not P, and then for P or P. And note that the column of P or not P is always true. There's not a single case in which the column is false. So that's a tautology. So P or not P is a statement that's always true, right? If I say that the sky is green or the sky is not green, that statement is always going to be true. And this relates to some of the exercises we've done, which I asked you, is an argument that has a tautology as its conclusion always valid? And the answer is yes, because the argument, the conclusion, is always guaranteed from the premises, but actually it's always just guaranteed because it's always true. It's impossible for the conclusion to be false. So it satisfies our definition, so it is in fact a valid argument. Okay, so we can finally get to our first probability rule, and this is called the tautology rule. This is the rule that tautologies are assigned probability 1. Now this is going to be a rule that I just stipulate. I didn't come up with it, but a rule that we will just stipulate. And then we'll stipulate 4 more, so we'll have 5 rules from which we can build all our probability theory, which is pretty amazing. Right? This is going to be the foundation. And so the first piece of our foundation is going to be this one. If the statement is a tautology, then it's assigned probability 1. In other words, it's certain. So in other words, if A is a tautology, then the probability of A is equal to 1. Now ask yourself, why would we want this? Well, because we want our inductive logic to cohere with our deductive logic, right? And statements that are certain should get 100% probability. Tautologies are certain. No matter what happens, a tautology is always going to be true. So we want to assign maximum probability to those statements. And maximum probability here is going to be 100%. Let's get back to our omega. Remember that omega exhausts all the possibility space. So what would a tautology look like in this space? So let's let A be a statement. So we represent A again with the circle in blue. So where is not A over here? Well, not A would be all the gray area, not including the blue area, right? Because A is just what's inside, so you can imagine what's California. California is A in the space of the United States, and not California is the rest of the United States. And so here, how would we represent A or not A? Well, in fact, it's going to be the whole space, right? A or not A is always true. So no matter where you land in the possibility space, you're going to end up in a true statement. So the probability of A or not A is equal to 1. And we can also, sometimes people write just the omega to refer to a tautology. So this is a visual representation of our first rule, which assigns tautologies probability 1. Great. Let's get to our second rule to build this foundation for probability. But before we get there, we have to introduce some terminology. And this is a terminology of self-contradiction. A self-contradiction is kind of the opposite of a tautology. It's a statement that is always false, no matter what the facts are. So remember, a tautology is true no matter what the facts are. A self-contradiction is always false. So again, an exercise, I really urge you to pause the video and think of some examples of self-contradictions. The most classic example, right, is P and not P. So remember, a tautology would be P or not P, but here P and not P is a self-contradiction. It can't be that the sky is green and the sky is not green, right, if you look at just one patch of the sky. Let's look at it in terms of truth tables. Here we have P, again, and not P. We draw the truth values. And then in P and not P, right, it's always false. So in other words, if C is a contradiction, then probability of C is equal to 0. And again, why would we want this? Well, because logical contradictions cannot happen. Let's see this in the probability space. So again, we have A and not A, and this, right, A or not A is a tautology, it's a whole space. But where is A and not A? Can you point it out to me? Well, probably you can't because it's not actually on the graph, right? There's nowhere in omega that you can point to and say, that's where A and not A is. A and not A just isn't on this diagram. And so this is a contradiction rule. Self-contradictions are assigned probability 0. And sometimes it's noted as P of this sign, which is called the empty set, but that's not so important, is equal to 0. And probability is equal to 0 is, again, the opposite of what probability is equal to 1 is. Probability equal to 1 means it's certain, so probability equals to 0 means that it's impossible. And so just as in omega, if the statement is a tautology and you point anywhere, it's going to be true. For a self-contradiction, anywhere you point, it's going to be false. So we want to assign those statements that are in a way certain not to happen, we want to assign them probability 0. Okay, so we've seen already 2 rules of our foundation. That's pretty cool, right? We just saw 2 rules that will allow us all the tools to bring up the house, if we want, of the inductive logic. Now let's get to our 3rd rule, which is a little bit more complicated, and again we have to introduce some notation, which you've already seen a little bit in the class, but let's remind ourselves. And this is the notation of logical equivalence. So what does it mean for 2 statements to be logically equivalent? Here's the definition. 2 statements are logically equivalent if they make the same factual claim. In other words, if they have the same truth values everywhere. So if 2 statements have always the same truth values, then they're logically equivalent. It doesn't mean necessarily that they have the same meaning, but it does mean that they have in some sense the same logical meaning in that they're both true at the same time and they're both false at the same time. So here's an exercise. Can you come up with an example of 2 logically equivalent statements? Again, I urge you to pause and to come up with one yourself. Well, a very simple example is that A and not A are logically equivalent. So let's see why. Let's draw the truth table for A. So that's true and false. Those are our only true possibilities. For not A, well, we just put we flip the truth values of A, and then we add the column for not A. So what we do is that we flip the truth values from not A, and we get the same exact truth values, right? If you look at the first column and the third column, they have the same truth values at the same time. Now, here's a question for you. Are all self-contradictions logically equivalent? Yes, they are, right? Because they have the same truth values everywhere, namely false. Similarly, are all tautologies logically equivalent? Yes, they are, because again, they're true everywhere. But these aren't the only examples of logically equivalent statements. So if 2 statements are logically equivalent, then they have the same probability. That's our 3rd rule, and that's called the equivalence rule. For example, the probability of A is going to be the same as the probability of not A. Why would we want this? Well, because they're true in exactly the same cases, right? They're true and false in exactly the same time. So we want, in a way, the same statements that have the same logical meaning to be assigned the same probability. Let's see this visually. Okay, so to represent this rule visually, let's ask ourselves, where is not A? Why are we asking this? Well, because we saw that A and not A are logically equivalent. So where is not A in this graph? Well, it's just the same as A. It's just the same in that it's true at the same time and false at the same time. So they occupy the same space. And since they occupy the same area in the space, they're assigned the same probability. And this is a visual representation of our third rule, which is the equivalence rule. If two statements are logically equivalent, then they have the same probability. That makes sense, right? Intuitively, you'd want statements that say the same thing to have the same probability. Cool. So we've seen 3 rules that are going to be our foundations. So we still have 2 to go for the rest of this class. And to start off with the 4th one, we'll go over the meaning of mutually exclusive. So the definition of mutually exclusive is the following. 2 statements are mutually exclusive if and only if they cannot both be true at the same time. So note, the condition here is that they can't both have the same truth at the same time, but they can both be false at the same time. So can you come up with an example of 2 mutually exclusive statements? So a very simple example, right? Let's just draw the truth table, and we see that they're never both true at the same time. But again, note, 2 mutually exclusive statements can both be false at the same time. Again, let's look at this visually, what it means for 2 statements to be mutually exclusive. Are A and B mutually exclusive here? No, right? Because it's possible for them both to be true. Where would that be? Well, in the cases where their circles intersect, right? Where there's a red dot here, that's a case where A and B are both true. So they're not mutually exclusive. Now, are A and B here mutually exclusive? Yes, they're never both true at the same time. But note that over here, where the red dot is, here is a case where they're both false at the same time. So it's not that they have opposite truth values, it's that they're just not both true at the same time. So what our rule is going to tell us, it's called the special disjunctive rule. It's going to say this: if A and B are mutually exclusive, right, only in cases where A and B are mutually exclusive, then we have the following rule. The probability of A or B is equal to the probability of A plus the probability of B. This does not hold for cases where A and B are not mutually exclusive. That's really important. So here's a dice example. Are the results of a fair dice mutually exclusive? Yes, right? The individual results are mutually exclusive. It can't be that the dice lands both on 1 and on 6 at the same time. So what's the probability of that the dice lands on 1 or the dice lands on 6? Well, it's a probability that the dice lands on 1 plus a probability that the dice lands on 6, which is equal to 1 6 plus 1 6, which is equal to 2 6. Now suppose we throw the dice twice. Is it the case that these are mutually exclusive, that the dice lands 1 on the first throw, and that the dice lands 1 on the second throw? Are these mutually exclusive? Can we do the following? Can we say, well, that this is equal to the probability that the dice lands on 1 on the first throw plus the probability that the dice lands on 1 on the second throw, which is 1 6 plus 1 6, which is equal to 2 6? No, we cannot. Why not? Well, because this rule only applies to cases where it's mutually exclusive. They can't both be true at the same time. So here the probability of A or B is equal to probability of A plus the probability of B. But if there's cases where they can both be true at the same time, it's not equal. In fact, it's equal to the following equation, which actually we're going to prove in the homework in next week. But let's prove something here in this class. Let's prove that the probability of A is equal to 1 minus the probability of not A. So we already have the tools, or we have 4 rules. I didn't give you the 5th yet, but already we have enough tools to prove something kind of interesting in probability theory, right? This equation. We have enough tools to say, like, a theorem of probability. It's a simple one, but still. So let's do that together. So we know that the probability of A or not A is equal to 1. Why do we know that? Well, by the first rule that we saw, which is the tautology rule. We also know that A or not A are mutually exclusive, right? I showed that to you. They're never both true at the same time. So what rule can we use here? Well, we can use the rule from the special disjunctive rule. So, which says that if 2 statements are mutually exclusive, and A or not A are mutually exclusive, if that's the case, then the probability of A or not A is equal to probability of A plus the probability of not A. Okay? We're just using the rules here. But now we can put these together, and we have that 1 is equal to the probability of A or not A, which is equal to the probability of A plus the probability of not A. And then we just shuffle things around with some very easy algebra, right? We just subtract probability of not A from both sides, and we get that the probability of A is equal to 1 minus the probability of not A. So we've proved a little theorem in probability theory already with our 4 rules. That's pretty neat. But now we can move on to our last rule. Our last rule is going to be maybe one of the hardest ones to conceptualize, but we've already introduced some of the basics in the past classes. Remember that P and Q are independent when these 2 arguments have the same inductive probability, namely when P therefore Q and not P therefore Q have the same probability. All right, remember that example I gave you? Whether I drink a glass of water today, therefore President Biden will rerun for president in 2024, or I don't drink a glass of water, therefore President Biden will rerun for president in 2024, right? The event of me drinking water and Biden rerunning for president, these are independent events, right? Their probabilities are not going to be meshed with one another. And this is the intuition that the last rule is going to take into account. And it's called the special multiplication rule. And it says, in cases when A and B are independent, and only in these cases, then the probability of A and B is equal to the probability of A times the probability of B. Okay? So only in cases where they're independent. This rule does not hold, just like the previous one does not hold if the statements are not mutually exclusive. This one does not hold if they're not independent. Now, are these 2 statements independent? The dice throw is even and the dice throw is odd. Are they independent? No, actually. They're mutually exclusive. But if one happens, then we know that the other one didn't. So we know that these aren't going to be independent, right? So if one happens, so if the dice throw is even, that gives us information about whether the dice throw is odd. And so this means that they're not independent. So the probability that the dice throw is even and odd is equal to 0, right? Because these are mutually exclusive. They can't both be true at the same time. And that's equal to 0. But that's not the same as the probability that it's even times the probability that it's odd, right? The probability that's even is 1/2 and probability odd is 1/2, right? So this is one way to conceptualize. So independence means that whether one event occurs or not is not going to give you information about the other event. So two statements are independent if they don't really give information about each other, right? Me drinking water gives you no information about Biden rerunning for president, but the dice rolling even gives you information about whether it rolled odd or not. All right. These are the 5 rules we need to build our probability theory. The first one, let's recap, says that tautologies get assigned probability 1. The second one says that self-contradictions get assigned probability 0. The third one says that equivalent statements get assigned the same probability. The fourth rule says that if two statements are mutually exclusive, then the probability of one statement or the other is equal to the probability of one statement plus the probability of the other. Now, if two statements, this is the fifth rule, if two statements are independent, then the probability of A and B is equal to probability A times the probability of B. Learn these rules, make sure you fully understand them, and from this we're going to build our inductive logic. But now already, we have some foundations of probability, and we've already proved some things, and you'll prove some things in your homework. So that's pretty exciting. Okay, thanks for watching.